Hello all. In this video, we'll learn about inference rules, determining closures, and minimal cover for the functional dependencies. Inference rules for functional dependencies. The set of all dependencies that include F as well as all dependencies that can be inferred from F is called the closure of F. It is denoted by F+. Here we have got two functional dependencies, that is SSN determines employee name, birth date, address and department number, and department number determines department name and department manager SSN. So using these two functional dependencies, we can infer some of the additional functional dependencies, like SSN can determine department name and department manager SSN. Yes, due to the rule called as transitive rule, we can infer some of the, not only transitive rule, there are 6 inference rule, we can infer some of the additional functional dependencies. Yes, let us look into some of those 6 inference rules. The first one is reflexive rule. Well, if y is a subset of x, then x can determine y. So which means, so this is a reflexive rule, states that a set of attributes always determines itself or any of its subsets. For example, the first name and comma last name can determine first name, which means attribute can determine itself. So that rule is called as reflexive rule. The second rule is augmentation rule. X determines y. Yeah, the augmentation rule says that adding the same set of attribute to both the left and right hand side of a dependency results in another valid dependency. Now, suppose if we add attribute to both left hand and right hand side, so that is a valid dependency. As you can see, xz determines yz, so it's a valid dependency. Let us consider an example whereas SSN determines the first name. So if I just add department name to both left and right hand side of the function dependency, so this is a valid dependency according to the augmentation rule. The next one is transitive rule. When x determines y, y determines z. So according to the transitive rule, x determines z. So yes, as you can see here, SSN determines department number determines department name. So according to the transitive rule, SSN determines department name. Yes. Next we'll look into the decomposition or project rule. Yeah. The decomposition rule says that we can remove attribute from the right hand side of a dependency. Applying this rule repeatedly can decompose the function dependency. Yes. As you can see here, x determines yz. So this can be written as x determine y and x determine z. So this is called as decomposition rule. As you can see here, SSN determines first name, comma, department number. So we can decompose the right hand side, that is SSN can determine first name and SSN can determine department number. Yes, the fifth rule says it's a union or additive rule. Yes, if I have a two functional dependency, that is x determines y and x determines z, so we can combine this to form x determines yz. Yes, it allows to combine a set of dependencies into a single functional dependencies. As you can see here, we have got multiple dependencies formed to a single functional dependencies. Yes. Pseudo-transitive rule. So if x determines y and wy determines z, then wx determines z. Determining x plus the closure of x under f. Okay. Let us consider the relation schema employee project. Here these are the three functional dependencies, that is SSN determines employee name, project number determines project name and project location, and SSN comma project number determines the hours. So there are three functional dependencies. So let us find the closure of SSN first. Now, as per the reflexive rule, the attribute can determine itself. So, yes, SSN can determine SSN, and based on the function dependencies, SSN can determine employee name. So, the closure of SSN is SSN comma employee name. Okay. Yes, what is the closure of project number? So, as per the reflexive rule, a project number can determine itself, that is project number, and then it can determine project name comma project location. Yes, project name comma project location, and the closure of SSN comma project number here is equal to, yes, as per the reflexive rule, it will determine SSN and project number. It will determine itself, and SSN determines employee name. Yes, SSN determines employee name, and the project number determines project number, project name, and project location. Yes, yes, project number is here, project name, project location, and the number of hours here. Yes. Yeah, just by finding the closure, we can identify the candidate key. So just by looking at this, we can make sure that the candidate key of employee project relation schema is SSN comma project number, because these two attributes, the combination of these two attributes determines all other attribute from the relation schema. Yes. Yes, let us solve this problem. Finding the candidate key using the closure method. Yeah. Yes. Let's say we have got relation schema R. Let A, comma B, C, D be the attributes of a table R. Let R be the table name, and A, B, C, D are the attributes of the table R. Okay. And we have got three functional dependencies, that is A determines B, B determines C, and C determines D. Okay. Now let us find the closure of each attribute A. Okay. As per the reflexive rule, A determines itself A. Yes. And we have got function dependency where A determines B. Yes. This is how we determine B. Okay. And yes. Yeah, we have got function dependency where A determines B and B determines C. So as per the transitive rule, A will determine C. Yes, so this is how we got A, B, and C. And since A determines C and we have got C determines D, so again as per the transitive rule, A determines C and C determines D. So as per the transitive rule, A determines D. So A can determine A, B, C, and D. Okay. Now, yeah. Now let us see. Let us find the closure of B. Yeah, B can determine itself based on the reflexive rule. Yes. As this is what is given. B can determine C. Yeah, as you can see, B determines C. So B determines C and C determines D. So based on the transitive rule, so B can determine D. Yes. So yeah, that's it about closure of B. And let us look into the closure of C. Yeah. Yeah, initially C determines itself based on the reflexive rule, and C determines only D here. Yeah. Yeah, now looking at finding the candidate key. Candidate key is the one which identifies all the other attribute. So I can, looking at this closure method, I can say A is an attribute that determines all other attribute, that is A, B, C, and D. Whereas B can determine only B, C, and D. It cannot determine A. Whereas C determines only C and D. So the candidate key is A. So that because it can determine all the rest of the attributes of the relation schema R. Yeah. Okay. Yes, next is equivalence of sets of functional dependencies. Okay. Two sets of functional dependency E and F. Now E and F are equivalent. So if closure of E is equal to closure of F, so therefore equivalence means that every functional dependency in E can be inferred from F, and every functional dependency in F can be inferred from E. So that is E is equivalent to F if both the condition E covers F and F covers E hold. Let me explain this equivalence sets of functional dependency with an example. Okay, yes. Yeah, let me consider these two functional dependency f and g. Now I need to find whether these two functional dependencies are equivalent or not. Yeah, to check whether these two functional dependencies f and g are equivalent or not, first we need to check whether functional dependency f can be inferred using functional dependency in g. Yeah, once again I repeat, so to check whether this f and g are equivalent, we need to check whether f can be functional dependencies of f can be inferred using functional dependency in g, and also functional dependency in g can be inferred using the functional dependencies of f. So for that, first let me calculate, let me identify, check whether f can be inferred using function dependency in g. So for that, take the attribute from left hand side of function dependencies in f. So as you can see here, I'll be just taking the left hand side of f, that we have is a, b and ac. So this is a, b and ac. So I just noted down the left hand side of the function dependency f, a, b and c. Now I need to find out the closure of a, b and ac using the function dependency g. Okay, so I repeat once again, I need to find the closure of a, b and ac using the functional dependency of g. Yes, so first, a can determine itself. Yes, this is based on the reflexive rule. Yeah, this is what we have got it. And a determines b. Yes, we have it. A determines b, and a determines b and b determines c. So based on the transitive rule, a determines c. Yes, this is about the transitive rule. And we have got a determines d. So I can say that a can determine a, b and c, d. Yes. Next, talking about b, closure of b. As you can see, b determines itself. This is a reflexive rule. And b determines c. Yes, b determines c. Yes. Now let us find the closure of ac. As you can see, ac can determine a. Yes, based on the reflexive rule, and ac can determine c, again based on the reflexive rule. And yes, ac determines a, but we have got a determines b, so ac determines b. Yes, and yes, again, as I can say that ac determines b, b and b determines c based on the transitive rule. I can say that ac determines c as well, and ac determines a and a determines d. So based on the transitive rule, I can say that ac determines d. Yes, so we have just got the closure of a, b, c based on the functional dependencies of g. So we need to just check whether we have deduced all the, whether we have just found all those functional dependencies of f. As you can see here, a determines b. Yes, we have got a determines b. So b determines c. Yes, we have got that functional dependency. And ac determines d. Yes, we have got it. Yeah, so yeah, our job is half done. So we can say that we can easily infer the functional dependency in f can be inferred using functional dependency in g. Okay, now let us check vice versa. Okay, now I'll be just taking the left hand side of g, that is a, b, again a, same thing. We'll be just taking the left hand side of g, and we'll be finding the closure of a and b using the functional dependencies of f here. Okay, yes, so here as you can see here, based on the reflexive rule, a determines itself. Okay, a determines a, and yes, based on this functional dependency, a determines b, and yeah, b determines c. So based on the transitive rule, a determines c. Yes, we have got this rule, and a determines d. So we just find a determines d just based on the additive rule or union rule. So let us consider these two, a determines a and a determines c. So according to the additive rule or a union rule, A determines AC. Okay, so again we have AC determines D here. A determines AC, AC determines D. Based on the transitive rule, A determines A determines D. I repeat once again, we have got, considering these two functional dependencies where A determines A and A determines C. So according to the transitive rule, A determines AC. Now here we have got one more functional dependency, that AC determines D. So based on the transitive rule, A determines D. Okay. Next, to find the closure of B, as we can see, B determines itself based on the reflexive rule of the inference rules, and B determines C. Yeah, B determines C. Okay. Yeah. Now let us check whether we have just deduced all the functional dependencies of G. We have got A determines B. Yes, A determines B. Do we have B determines C? Yes, B determines C. We have got it. And A determines D. Yes, we have got it. Now I can say that both F and G, both these set of functional dependencies are equivalent, because we just inferred using, you can see over here, we just checked whether the functional dependency in F can be inferred using functional dependency in G. Yes, we have done it. And here, using the functional dependency of G, we just inferred the functional dependency of F. Yes. So that's it about this equivalent. We just found this, the two sets of functional dependencies F and G are equivalent. Yes. 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 Let us consider these two sets of functional dependencies, and let us check whether these two functional dependencies are equivalent or not. Yeah. To begin with, we need to check whether functional dependencies in X can be inferred using functional dependencies in Y. And again, from here we need to check whether functional dependencies in Y can be inferred using functional dependency in X. Okay. Yeah. To begin with, the first, we need to just take the left hand side of the sets of functional dependency X. So that is A and B. Okay, we need to find the closure of A and B. Okay, and we need to find the closure of this A and B using the functional dependencies of Y here. Okay. Yes, so for that, let us find the closure of A. Yes, A determines A, that is based on the reflexive rule. A determines A. Okay, A can determine itself. So now next, first functional dependency what we have is A determines B. Yes, A determines B. Yes, the next function dependency what we have is A determines B and B determines C. So using the transitive rule, A determines C. So yes, A determines C. And third function is functional dependency is A determines C. Yes, that's it. We have determined that C also. Okay. Next is to find the closure of B using the functional dependency of Y. Okay. Let me erase all. Yes. Yes, as per the definition, we have definition of reflexive rule. Attribute can determine itself. So B determines B, and here we have B determines C. Yes, it will determine B determines C. Okay. So now it's time to check whether functional dependencies in X can be inferred using whether we have inferred using functional dependency of Y. Okay. Now let me verify whether this function dependencies have been inferred. So here we have got A determines B, even A determines B, and whether B determines C. Yes, B can determine C. So hence, as you can say, we have done with the half part. So again, now we need to verify, we need to check whether whether functional dependency is Y, whether we can be inferred using functional dependency in X. Okay, now let me take the left hand side of the functional dependency, that is A, B and A. Okay, this is not required. So A and B. So we need to find the closure of A and B using the functional dependency of X now. Okay, so A determines A, yes, using the reflexive rule, and yes, A determines B, yes, as you can see, A determines B, and B determines C. Based on the transitive rule, yeah, A determines C. Okay, now let me find the closure of B using the functional dependencies of X. Yeah, B determines B using the reflexive rule, and yes, it is given here, B determines C. Yes, now let me cross verify it with the functional dependencies of Y. Yes, whether A can be determined, whether B can be determined by A. Yes, it is over here. Let me erase it. Yes, now we need to just verify whether A can be determined by, whether A determines B. Yes, A determines B here. B determines C. Yes, the B determines C, and A determines C. Yes, now I can say that both the two sets of these functional dependencies are equivalent. Okay, the next is finding the minimal sets of functional dependencies. Yeah, the set of functional dependencies you have to be minimal if it satisfies the following condition. Okay, so the first condition that every dependencies in F has a single attribute for its right hand side. Yes, so the first condition, the first criteria for the minimal sets of functional dependency is every dependencies in F has a single attribute for its right hand side. A right hand side should be always single. Okay, we cannot replace any dependencies X determines A in F with the dependencies Y determines A, so whereas Y is a proper subset of X. Okay, yes, so for the final minimal functional dependency, there should not be any redundancy. When I say redundancy, it shouldn't have, like, it cannot be replaced, like X determines A in F with the functional dependency Y determines A. Yeah, we cannot have a redundant attribute, a redundant functional dependencies in the set of minimal functional dependencies, and we cannot remove any dependency from F. So this is what we say it as a final minimal functional dependencies. So these should not be available, like there should not be any redundancy, we cannot remove any dependencies from the set of functional dependency, and the right hand side should be always single. Okay, let us look into the algorithm of a minimal cover. um, yes um, yes, that set F is equal to E. Now replace each functional dependency. Now what I said was in the previous the points in the previous criteria, where right hand side should be single. As you can see here, we need to split the right hand side to, X determines A1 to AN. We just split it as X determine A1 and X determine A2 and X determine till AN. So this is what we just split the right hand side of the function dependency. Okay, next is for each functional dependency X determines A in F for each attribute B that is the element of X. Yeah, the B should be the element of, B is an element of X. Now yes, yeah, we have got a function dependency. The F is a set of function dependency minus X determines A. Okay, which means out of the set of out of the sets of function dependency, if I just remove that X, this function dependency X determines A, and again perform a union operation, and the same function from the same function, I'm just adding a same functional dependency, but from that X I'll be just removing B. Well, if this is equivalent to the functional dependency, to the previous functional dependency, then replace X tends to A with X minus B tends to A. Once again I repeat, so the overall intention is there should not be any redundant functional dependencies in the set of functional dependency. Once again I repeat, here F is the set of functional dependency. Here I'm just removing out of that set of functional dependency, I'll be just using a minus operator, I'll be removing this functional dependency, that is X tends to A, and again using the union operation I'll be just adding it, but while adding it from X from the x attribute, I'll be just removing the b. I'm performing just x minus b, but still if this it is equivalent to f, then I will replace x tends to a with x minus b tends to a. So this is what we just remove the redundant function dependencies. Yeah, next is for each remaining functional dependency x determines a in f, if x minus yes, if I just remove x tends to a from the set of functional dependency f, still if it is equivalent to f, then remove x tends to a. Okay, again this is what redundant this is what overall it is removing the redundant functional dependencies. If an overall functional set of functional dependencies, if I remove that particular functional dependency that is called as x determines a, and well, if this is equivalent to f, then I will just remove it. Even if I remove x determines a, but still if it is equivalent to f, then I have no need of this x determines a from f. I will just removing it from the f. Yeah, this is just an algorithm for the minimal cover f for a set of functional dependency e. Yes, let me remove the erase it. Yeah, I'm not able to erase it. Fine. Yeah, now yeah, find the minimal cover of e for this functional dependencies. Yes, as you already learned in the first step, the right side should be always single. Break down the right hand side of each functional dependency into a single attribute. Here are the right hand side. Yes, here all the right hand side is always single, so I guess you can skip first step. Yeah, so we need to find the minimal cover for this given functional dependencies. Okay, the first step is to the right hand side should be single. Yes, here all the attribute of the function right hand side of the function dependencies is single. So yes, I'll be just skipping the first step. Second step in the second step, I'll be just concentrating on the left hand side. I'll be, yes, here left hand side b is single, fine, leave as it is. Again here d is also single, leave as it is. Yes, here we have ab tends to d. So now try to make try to make a determines d or b determines d. Just find out whether there is any redundant attribute in this functional dependencies. So for that, check if ab determines d has any redundant attribute on the left hand side. So that is, it can be replaced as b determines d or a determines d. Yes, yes, to in order to convert this b determines d or a determines d, we have got just ab determines d, yes, and we have got yeah, we have got b determines a. We can make use of this, as you can see here. We can make use of this b determines a. Yes, if I just augment b to both the side, that is based on the augmenting rule or additive rule, as you can say, if I just add b to both the side, see, by augmenting rule, so consider b tends to a, by augmenting b on both side, we get bb determines ab. Okay, anyways, we have ab determines d. Okay, so I can say that b determines ab and ab determines d. Then based on the transitive rule, I can say b determines d. So I got this, I got b determines d. So hence by the transitive rule we get b determines d. So because a determines ab and ab determines d, so we now we can just modify e, that is b determines a as it is, keep d determines a as it is, and you just, yeah, and as you can just see here, ab determines d, you can just change it as b determines d. Okay, yes. Yeah, now next, third step, we need to find whether there is any redundant function dependencies in the given whether there is any redundant function dependency in this set. Okay, as you can see, b determines a and d determines a and b determines d. Yes, yeah, as you can see here, B determines D here and D determines A. Yes, as you can see here, this B determines A is redundant, isn't it? Once again I repeat, B determines D and D determines A. Based on the transitive rule, we get B determines A, but that particular function dependency is already available. So this is what we call as a transitive dependency. So this is called as redundant function dependency. So hence B determines A is redundant in E and can be eliminated. This we can be eliminated. So the final minimal cover E for the given function dependency is B determines D and D determines A. Okay. Yes, we have got one more problem on minimal cover. So we need to, yes, we have got this set of function dependency where we need to find the minimal cover for G. Okay. Based on the first step, first step is about breaking the right hand side. Yes, just decompose the right hand side, that is A determines B, yes, A determines C, and A determines D, and A determines E, and again here, yeah, the CD, the left hand side, you can keep it as it is. Yes. Now in the second step, yeah, we need to concentrate on the left hand side. We need to try to split this. Okay, we need to try to split CD. Either C determines E or D determines E. Yes, yeah, as you can see here, um, in the left hand side we don't have either C or D. We have got A, and again we have got A. So I think it's not possible. Let me check. For CD determines E, neither C nor D is erroneous on the left hand side, since we cannot show that C determines A or D determines E, C determines E or D determines E from the given function dependency. Yes, for that we need to just check, just by looking at the set of function dependency, we can make sure that we cannot split CD as C tends to E and D tends to E. So hence we cannot replace it, keep it as it is. Okay. Well, now third steps, we need to check whether there is any redundant function dependency in the set. Yes, as you can see here, yeah, since A determines CD, as you can see here, this is an additive rule. A determines C and A determines D. Based on the additive rule, I can say that A determines CD. Yes, A determines CD, and CD determines E. Once again I will just erase it. I'll erase it everything. As you can see, in the third step we need to remove the redundancy. Okay. Yes, we have got this two function dependencies. Based on the additive rule, A determines C and A determines D, it will become A determines CD. Okay, like this, A determines CD. And as you all know, CD determines A. CD determines A. So by the transitive rule, we all know that A determines E. Well, we have got a redundant, so this is a redundant. A determines E. So we can just eliminate this, that is A determines E, and keep rest as it is. What is it? A determines B as it is, A determines C, A determines D, and CD determines E. Yes, this is the final minimal cover which we got, and we just added it. That is A, B, C, D. A determines B, C, D, and C, D determines E. So this is the final minimal cover. Okay. Yes, we have got one more problem here. Find a minimal cover. F is equal to A tends to C, AC tends to D, and E tends to ADF. Yes, based on the first step, we need to break the right hand side. Yeah, here right hand side is C as it is. Here right hand side is D. Okay, and here the right hand side is ADF. So we need to convert it as A tends to A tends to D, and A tends to F, like what we have done it over here. Same way. Yes, we are done with the first step. The second step is we need to concentrate on the left hand side. As you can see, the left hand side we have got AC. So we need to try to make it as A tends to D or C tends to D. Yeah, as you can see, we need to replace AC to try to replace AC tends to D to A tends to D and C tends to D. For that we need to just concentrate over here. Yes. Yeah. By augmenting, you can just have a look at this. A tends to C. By augmenting A tends to C with the both the side with A, so what happens is when I add A to both the side, what happens is we get A tends to AC. Yeah, which is also same as A tends to AC. Okay, and yes, whenever A tends to AC, we have got AC tends to D over here. So based on the transitive rule, we have got A tends to D. Okay, so I can say we have got A tends to C, A tends to D, E tends to A, E tends to D, and E tends to F. We just got A tends to D, not C tends to D. Okay, now we need to, in the third step, we need to check whether there is any transitive, whether there is any redundant functional dependencies. Yes, we have got A tends to C, A tends to D, E tends to A, E tends to D, E tends to F. Yeah, as you can see here, we have got, once again, let me erase all. Okay, as you can see, we have got E tends to A, and we have got A tends to D. So E tends to A, E determines A determines D, so E determines D. So this is called as redundant functional dependencies, because E can determine A and A can determine D here. So based on the transitive rule, E can determine D. So when this can determine E, when this here in these two functional dependencies, we can determine E can determine D, then this is redundant. Yeah, as you can see here, E determines A and A determines D, so we derive E determines D. So hence E determines D is redundant and can be eliminated. So what is remaining? That is A tends to C, A tends to D, E tends to A, and E tends to F. So this is the final cover for the given set of functional dependencies. Yes, the first thing we should know, first very important here is, in the first step we need to break the right hand side. Yes, in the second step we need to try to make it as A tends to D or C tends to D. This is what, either we need to try to make A tends to D or C tends to D, if it is possible only, if not, okay. And in the third step, we need to remove the redundant functional dependencies. For that, we need to make sure you should know the inference rules. Okay. Yes. Yeah. Suppose that you are given a relation R. R is a table name, and we have got attributes called as A, B, C, D, E with the following functional dependencies. So we have got three functional dependencies, that is C, E belongs to D, D belongs to B, and C belongs to A. Okay. Find all the candidate keys. First, as you can see here, yeah, from the given set of functional dependencies, we can observe that only the attributes C and E are present only on the left hand side. So hence we can try with C and E attribute to find the candidate keys. Yes, C alone cannot determine all the attribute. As you can see here, C determines A, and yes, C, E determines D, and D determines B. So what and all we have got totally 5 attributes. So if I consider CE can determine CE can determine A, CE can determine D, and CE can determine B. So hence I can say that the CE itself is a candidate key, because what is a candidate key? Candidate key is an attribute that determines all the attributes. Okay, the one thing I can say, based on the reflexive rule, as you can see here, CE can determine A. Okay, as you can, this is what we have done, and CE can determine D, CE can determine CE determines D and D determines B, which is also known as, based on the transitive rule, CE can determine B as well. So yes, CE can determine itself, that is C and E. So CE here is a candidate key. Yes, this is the last problem. We have got a relation name, table name called as R. A, B, C are the attributes, and we have got the functional dependency where A determines B and B determines C. Find a candidate key in R. So candidate key is an attribute where it determines all other attributes. Here we have got A that determines B, and B in turn determines C. So I can say that A is what candidate key. Here B is determining only C and C is not determining anything. So here A is a candidate key. Is it so? Yes, A is a candidate key here. Okay. Is R, let me clear it. Let me clear this. Yeah. Is R in BCNF? Justify answer. Okay. Yeah. Here R is not in BCNF because it is not in 3NF. What does 3NF says? There should not be any transitive dependency, but here there is transitive dependency where A determines B and B determines C. So there is a transitive dependency. So hence I can say that R is not in BCNF. Okay, so not because it is not in 3NF. Find the possible violation of BCNF for R. Yes, as you all know, BCNF means whenever function dependency occurs, x tends to y occurs for the non-trivial function dependency x tends to y, x should be the super key. Here, as you all know, A is a candidate key. As you can see here, B determines C, and here B is not a super key. As you can see here, B determines C, and B is not a key. So yeah, this is a possible violation of BCNF. Let us look into the fourth question. If R is not BCNF, give a decomposition of R in relation that will be in BCNF. Yeah. So for that, yeah, since B tends to C, this is what this function dependency is violating. Let me clear it. So what is violating here is BCNF is B determines C. So for that we need to split BC separate, make BC separate, and keep AB separate. This is how decomposition works. Yeah, that's it about this video. Thank you for watching this video.